Good morning, everybody. Welcome back to another edition of Chemistry 101, the quantum nature of atoms and electrons and all that kind of good stuff. So, thus far we haven't even begun talking about atomic structure or electrons or anything, and we're still not gonna, because we still are gonna be digging in just a little bit, these little steps in our knowledge so we can learn about or understand how they behave before we can really dig into talking about them. And I know you're also thinking, Stu, what happened to the bow tie? Well, today I thought I'd wear this t-shirt because I don't get to wear it often, only periodically. I wear this t-shirt periodically. Get it? Because guys, that's hilarious. Seriously. But do you know what's not hilarious? This. So look, today what we're going to dive into is the Bohr model of the atom, because this was a bit of a breakthrough. It's not the end all and be all, and his model worked pretty good for hydrogen, where it was super simple, one proton, one electron. And we actually learned a lot about atoms and electrons and how they work from his work. It hasn't stuck though, because there were little problems. Which is kind of how things go historically, right? We have this new theory, we have evidence that supports it, and it works really well, most of the time, but there are little cracks in the theory. And so what happens is other people are yeah, there's little problems there, and the person Bohr would be like, I know, but it works perfectly for hydrogen, but not for other stuff, so I don't know. And as we dug into those things a little more, as we tried to figure why, it took us to the next step. You know what I mean? So Bohr put us up quite a step, moved us forward quite a ways with this, and it all started out with these things, the bright line emission of hydrogen. So basically, what dude did was he took a tube full of hydrogen and he zapped it with a lot of voltage, it's 5,000 volts, I think, is the one that I have in my classroom. So a lot of voltage. And again, voltage is just well, maybe not again, but voltage is the amount of force that it takes that you're applying to move electrons. It's not the amount of electrons. So voltage won't necessarily kill you. Voltage is just how the analogy that I like to make with electricity is with plumbing, because electricity and plumbing work a lot the same way. So voltage is the force of the pump, right? Amperage or amplitude, that's the amount, or the amount of charge that's flowing. That's the amount, the flow of water. So you can have a huge pressure coming out of a little teeny, very, very small tube, and so not much water will come through, right? So you can have a high voltage, but not a whole lot of electrons flowing, and so that really won't hurt you. What hurts you is the amount of electrons going through. That's what will actually cook you. But that's neither here nor there. But right over there, you'll see we have this tube full of hydrogen, right? And a lot of high voltage. And what happens is they start to glow. Why? Because at that point the electrons are flowing through it. Slam one electron into the other. Electrons they go from the ground state to the excited state. And just like anything else that's thrown up in the air, it falls right back down. And so electrons absorb energy as they jump up, and then as they fall down, they release energy. When they release energy, they release it in the form of light. And so I don't know if you remember, hydrogen was this sort of beautiful purpley color that we have over here. And what he did was there was a tube, and then he made a very small slit, which is what they did back in the day is they would take a piece of glass and they would basically hold it over a candle to get carbon. You know how soot, you can put a candle over something, it makes a black mark on top, it's just soot. Then they take a razor and just go and take a razor blade and make a very, very narrow slit. And then, because of what it was sort of old-timey, an old-timey laser, it gave him a very narrow beam of light. And with that very narrow beam of light, he put it through a spectrum. Because they were whoa, what is going on? Why does hydrogen look purple? And they knew that these things, the prisms would actually prisms actually broke the light down, into its component wavelengths, right? And we knew enough at the time to talk about wavelengths and whatnot. So they were what is what is the purple light of hydrogen actually made of? Oops, sorry guys. So, whoa, where did my thing go? Oh, there it is. So, tiny little slit, they put it through the spectrum, and lo and behold, they did not get a rainbow. Like, not even close. What they got were these little, like, lines, right? They did not get a rainbow. And that sort of, like, broke their brain. Like, how is it at all even possible to get, like, light and then these lines? And so if they lined it up, if they put it out on a scale, they would get a purple, a blue, a green, and a red. And this is, down here is the wavelength of light. And they're like, dude, what is going on with this? Like, how is it possible that we're getting just one little beam and then nothingness and then one little beam of light and then nothingness and then one little beam of light and then nothingness? Like, it made no sense at all until Bohr came along. And you have to remember, Bohr was like, Bohr was kind of a genius. Not kind of, he absolutely was. Niels Bohr was like right up there with Einstein. He's Max Planck, Niels Bohr, these guys are all right there with Einstein. These were Einstein's counterparts. They were never quite as famous as Einstein. Einstein, his work was just beyond, but these guys could go toe to toe with Einstein, and they did. And Max Planck actually like said stuff that Einstein didn't agree with, but Max Planck, he was right, and so was Niels Bohr. And Einstein at the time was like, I don't like what you guys are doing. But they were like, evidence, and Einstein was still like, ugh, I don't like that. But there you go. So Bohr was basically like, why? This makes no sense. Why? And so they went further and further. They didn't do just hydrogen, but Bohr began his work with hydrogen. And oh yeah, this thing. Remember, every individual element gave its own unique, what we now call bright line spectra, right? Spectra being like, rainbows, right? So the elemental spectra are atoms spitting out rainbows. And when they discovered is that every single element did this. Every element gave these lines, right? It wasn't a smear of colors. Like if you take sunlight, if you do this with sunlight, you don't get these lines. You get a smear of color. Ish. I mean, one little caveat is that if you made the wave or the spectrum big enough, you could break it down to these little like lines, but not typically. You know what I mean? Like under the same circumstances, the sun would give you a big smear, but cadmium would give you just a couple of these lines. So the big question of the day was, what the heck is going on? Why are we getting just these lines? So Bohr came up with this idea that electrons lived in like orbitals, like orbits. Now Bohr straight up was like orbits, these like circles. Like, so he thought, okay, electrons are going around in circles. Where did he get this idea? He looked at the rest of like the universe, where you see things circling things, like planets circling suns and moons circling planets, and then there's like multiple stars circling around each other, and all the stars are swirling around, circling in these galaxies. So he's like, why wouldn't electrons circle the nucleus? Well, because they don't. So what he said was, here we have the nucleus right here, and then there are energy levels, and we call them like n equals 1, n equals 2, n equals 3. So I guess we're calling this one n equals 1. That's our first energy level. Here is n equals 2. It's our second energy level. Here is n equals 3. It's our third energy level. And the nucleus is just so stinking small you can't even see it. I think the analogy is like if you take a football stadium, not just a football field, but an entire stadium. That's the size of an atom, right? So the electron cloud would extend all the way out to like the edges of the biggest nosebleed seats. That's sort of like the cloudy edge. How big is the nucleus? It'd be in the middle, and it would be about the size of a marble, maybe even smaller. So mostly nothingness. And so what he theorized or tried to show, and he backed it up with math, by the way, that so it could be very predictable, was that electrons would give up energy as they went from high energy level boop, down to low energy level. And they would give up this energy in the form of a photon. Do you get what I'm saying? And what he said and what he predicted and the math that he came up with was that the energy of this photon was directly related to the energy difference between like the energy level where it started and the energy level where it finished, right? The difference between like final minus initial. So the energy difference between these two energy levels, or these two like orbits of the electron, is the exact amount of energy contained in that photon that was shot out of the atom. You guys get what I'm saying? And because every atom, or every element has a slightly different setup or configuration of electrons, that's why every atom has a slightly different like set of photons being spit out. Because these energy levels are different for each atom. Because if you think about it, they each have a different like kind of shielding. Do you guys remember shielding from regions? It's right. Okay, so the nucleus is right. So I can't deal with this, man. I can't deal without seeing a nucleus. So here I'm gonna make a nucleus. Right there. There's my nucleus. Okay, so here's my nucleus. This is my energy level 1. This is my energy level 2, right? So what that means is, so this is where all the positive pull is coming from, right? That's where all the protons are. So these electrons, right? They have to see or like get through this cloud of electrons. And if you remember, electrons are like clouds. So, oh geez, hold on, time out for technical difficulties here. So the electrons are actually clouds. Man, so much difficulty here, guys. It's like I'm suffering, but I'm not. I'll live. So like this thing, we draw it as a line, but really there's like it's a cloudy layered fluffy ball of fluff, right? It's like a cloudy cloud. So this electron, let's look at an electron. We'll look at this guy like right here. For this electron to experience the proton pull from the nucleus, it's sort of blocked by this cloud of these two electrons. That's what we call shielding, right? And so there's more than just this one electron. There's like a whole bunch of electrons all through here too. And so this guy way out here is like, it's not only does it have to get through this layer of clouds, electrons, it also has to get through this layer of clouds before it can get into and see that positive pull from the protons. So every atom had, oh, and also inside this layer, we're going to dig into this, there are other sub-layers that we call orbitals that this thing has to get through. So there's, each atom has its own unique set of like clouds that it has to get through, which is why each element has its own unique layer or like set of like photon emission, because they each have a different set of like shielding to try to get through. So all the energies are completely unique to each electron. So when we shine energy, or when we shoot energy into these atoms, the reason why each element is able to put out its own unique spectrum is because each element has its own unique energy levels because of how each electron is populating its like the things. Do you guys get what I'm saying? I don't know. Maybe you do, maybe you don't. We'll figure it out. So what Bohr theorized, each electron can only have a specific energy amount or value, what we call quantized, right? It's not a blur of like all the possible energies. Remember, we learned before with Niels Bohr that energy comes in packets. So it's going to have to come in a certain quantity or number of packets. It can't be like whatever energy you want. Do you get what I'm saying? And the light, so light is emitted as the electron moves from a high energy level or an excited state to a lower energy level, finally landing back on the ground state. And so that's where we get all these things. And here is basically that energy. So like the energy the energy of an electron in a specific ground state. Man, this is so annoying when I want to change colors, but I got to so I can like see from my own brain. So this says E sub n, right? So Niels Bohr came up with this thing. The energy of an electron in the particular energy level is equal to this constant. Cat. It's equal to this constant multiplied by 1 over energy level squared, like energy level being 1, 2, 3, that kind of thing. And it turns out to be 1, 2, 3 because it's like a logarithmic thing. Like it's an inverse square. Why? I don't know. Simply because nature. So if this is the energy, so what you can say is, as this thing goes from n equals 3, right? Because this is the third energy level, all the way down to n equals 2, right? Our delta energy is going to be equal to final minus initial. So this is n equals 3, that's our initial energy, and n equals 2, that's our final. Well, how do we find the energy of an electron in n equals 3? Well, right here. We make that the number 3. And how do we find the energy for our initial? Well, it's minus r sub h 1 over 2 squared. You dig? So that's that. That's how you figure out the energy transition. Oh, yeah, the Rorty theory. There it is. Yeah, again, look it up. Don't memorize it. It's, you know how that goes with like the whole mathing thing. So, this, I want you to see, it's an inverse square of your energy level, which means that like the energy level, like the difference between going from energy 1 and 2 is huge compared to 2 to 3, and then 3 to 4, 4 to 5, 5 to 6. Now why is that? Well, because nature. This is how most forces work in nature, and you can feel it, like you can experience and actually feel, like get a tactile feel for what this kind of energy transition means as far as distance goes. If you take a kitchen magnet and you hold on to it, and if the refrigerator is here, you take the magnet, pop the magnet right on, and then pull it off just a little tiny bit and try to hold it like just one paper width away from your refrigerator. And now you pull it just a little bit more and just a little bit more, and you'll feel that force like drop off precipitously or like dramatically, right? So very close, it's very strong, but like the smallest amount of change in distance has a huge effect in the force, right? So you can feel how this force sort of changes. Do you guys get what I'm saying? And that's how it is with the electrons and protons. They are sort of the same exact way. Pause. Stupid telemarketers. And so the energy that this so if this electron goes from this, this is energy level like what do we got here? This we'll call this energy level 1. This is energy level 2, energy level 3, energy level 4, energy level 5. So if we go from 5 to 4, right? And this electron goes from here to here, the energy, we can measure it one way, right? So the energy of that photon is equal to the Planck's constant times the frequency, and that's how we figured out how much energy it had, right? Right. Now, we can work backwards to try to figure out like what energy level it came from. Does that make sense? Do you guys get what I'm saying? So also, if it went from here to here, right? Max Planck times frequency. So that's why there are a couple things. One, that's why there are so many different like lines, because you can have a line going from 2 to 1, from 3 to 1, from like 3 to 2. So if you excited an electron from energy level 1 to 5, there are a lot. There's 1, 2, 3, 4, 5, 6, 7. I don't know. There's a lot. Every transition can be calculated with this. Are you guys picking up what I'm putting down? I'm getting a little bit ahead of myself. But every step, every change, whether it's from 4 to 5, from 5 to 4, from 4 to 1, like every single step has an emission. And they all kind of come in their own little categories. Ours, the visible light, is in what we call the Balmer series, which is like an energy wave, like an energy transition within one little group. Or hold on, hey man, what's up? All right, Olive made me pound cake. I won't make you watch me eat it. So good. So what I was saying before is like your transitions from like 5 and 6 down to 4, like with this kind of energy, with like this much energy, we call that what, the bracket series, the passion. I don't know how to pronounce it. The Balmer. It's named after scientists who like really studied it. Oh, that girl can cook. It doesn't really matter for us. These are just like names of different series. So they might give you like a transition or like an energy level, like, oh, an electron went from like energy level 4 to energy level 2. What series is this from? Well, it's from the Balmer series because it went from like 4 to 2, something like that. I don't really care about that stuff. What is important for us is that stuff right over there. That the energy of a photon during a transition is, just like I said, it's the change in energy from the energy levels, and it's always calculated the final energy minus the initial energy. You guys picking up what I'm saying? Awesome. I hope so. So if you remember, just like I said in that last slide, the energy of an electron in an energy level is calculated with this equation. So we're going to give our energy level a notation of n sub f. All right? And so guess what we're going to give for our initial energies? N sub I. So remember, we're just kind of exploding the very basic idea that the change in energy is equal to final energy minus initial energy. Well, the question is, what is final energy? Or how do we calculate final energy? Before, with like thermodynamics, the final energy was like the heat of formation for all of our products. And we put that into the equation. Same thing, only a little bit different. We are defining our final energy with this equation. And then our initial energy is being defined with this equation. And what is unique to each one is going to be what energy level our electrons are on, or at, or going to, or from. And so, if you do that, if you do like final minus initial, you get like an equation, and it's squared, and then this is like distributed through it, and so you can then take it out, and so you just simplifying it, we get this is our equation for the transition of an electron from our final to our initial. Why did it get flip-flopped? Because algebra, if you want to go in and do all the math you can, you just do like this minus that, do some flippity-dippities in basic algebra. What I care about is that you guys know that this is how we are going to calculate the amount of energy a photon has when it transitions from this energy level to this energy level. Get it? Got it. Good. Also, you don't necessarily need to memorize it. It's in your book. Just know that that's how we find it, right? So if you're given like 2 energy levels, that's how you're going to find your whatchamacallit. So for this one, if it goes from energy level 2 and drops, ooh, that's a bad, whoa. Maybe we should just stick with like what's there, the dark line. What we're going to do, like the way we would like, oh, whatever. Let me go back here. So what we would do here is if it went from 2 to 1, our final is 1, so we will put the number 1 squared right there. The initial was 2, so we would have 2 squared, and then we would like math it out. That's our constant, and that's it. That's your energy. And once you have the energy, like once you know the amount of energy, you can then go, wait, E equals H times frequency, right, dude? So you can predict which is what Bohr did, you can predict like what you think you're gonna get from like one energy to the next, and then you can go back and actually measure it. Right? You can like measure it by seeing what frequency it is. And as far as Bohr was concerned, he killed hydrogen, man. Like every single bit of like this whole thing, this all lined up beautifully and perfectly for hydrogen. For hydrogen. Yeah. Here we have. I just put this in here just to like, I don't know why. Here's the series, and here is like the area that it's of light that comes out of it. I never get too worked up about it. But this is where we are going to get worked up. Mapping. Oh boy. So the question is, what is the wavelength? So here our wavelength is what is in question. What is the wavelength of a photon in nanometers? In nanometers. Emitted during a transition from n equals 5 to the n equals 2 state of the hydrogen atom. So I got it right here. So my initial is 5, my final is 2, so it's not going all the way down, or maybe this is all the way down to ground state. I don't know. Okay, we're going to need to map this out, I think. So the first thing I'm going to do, maybe I'll do my mapping here, is first thing I'm going to do is I'm going to find the energy of the photon. How am I going to do that? I'm going to do that using delta energy equals energy final minus energy initial, and the energy of my energy level state there, right? The next thing is I'm going to find the wavelength using speed of light is equal to wavelength times frequency. Wait, no. Will that work? No, that's not what I'm going to do. I'm going to do... how am I going to do this? Can I find... no, I guess I can't do that next. Because the next thing I have is energy is equal to Planck's constant times frequency. So I'm going to have to find frequency using that. Third, I'm going to find wavelength using speed of light is equal to wavelength times frequency. And then fourth and final, I'm going to convert meters to nanometers. Man, that was easy. Well, that's kind of the thing, guys. Sometimes I'm wrong too, which is why I stop and think it out. That's why I do this like the mapping out, because the numbers are going to get stupid and weird. So before you do the math, think out your roadmap, and that like right down there, guys, that's all of it. Like that's like everything is right there. The rest of it is just like typing it into your calculator. So that's what I'm going to do once I go get my calculator. So all right, you guys ready? Let's go. Let's get to it. All right, so the first thing we need to do is find the energy of the photon during this transition. And that equation is going to be nope. Wait. Yep. That one. RH 1 over N I over NF squared. So, let's get to it. Well, where did I? Maybe I'll go. Okay, here we go. So, the change in energy is equal to, wait, I wrote it down here. RH times, yep, initial minus, I meant to double check that, yeah. It kind of switches when you do the math. So this will be equal to, again, doing math ahead of time so I don't screw everything up too bad. Although I can't guarantee that I'm not going to screw it up again. 18. Okay, so 1 over 2 squared is 4 minus 1 over my initial is 5 squared. Type this into my calculator. And I'm going to pause you guys while I do that so you don't have to watch me type my calculator. Okay, I'll be back in a second. Okay, so this left me with 4.578 e to the minus 19. The only units that are going to be here are joules, because these are energy levels, absolutely unitless. The units for this constant are joules, and so I'm left with joules. Pretty small amount. It's good because we're talking about one photon, right? So that's the energy of my photon. It's kind of easy, right? I mean, it's not terribly difficult. The tricky, I'm going to tell you right now, the tricky part is when you type this into the calculator, you got to put these fractions into brackets, so it's going to be like a double brackety thing. That's where most mistakes that I see happen. So that's how many joules. That was step number 1. Step number 2, the energy of that photon is going to be equal to Planck's constant times frequency, and that is how I'm going to find the frequency that will get me to the wavelength. So I've got 4.578 e to the minus 19 joules equals Planck's constant, which I can never remember. Oh, what is it? Is it 6.63? 6.63 e to the minus 34, and there's my unknown. You guys get what I'm saying? So I'm going to divide both sides by Planck's constant, and I'll be back in like 3 seconds. See, I'm making like a 2-hour video into like maybe only 1 hour. Dang it, hold on. All right, here I got frequency is 6.90497. I'm just going to stop there. That's way more than enough significant figures. Here's the important part, e to the 14. Since it's frequency, this will be hertz. Right. So step 1, I found the energy. Step 2, I found the frequency. So step 3, I'm going to use a good old speed of light is wavelength times frequency. So that's 3 times 10 to the 8th. 3.00 technically is equal to wavelength times 6.90497 e to the 14th. Gosh, I hate when it does that. And so my wavelength is equal. Pause. All right, it's 4.3446920 e to the minus 7 meters, and we know that meters are not a good way to measure the length. So actually, number 4 I'm just going to put right here. 1 nanometer is 1 times 10 to the minus 9, and you're going to stick around for this one. Perfect. There. I hope I got that one right. But you see how that works? It's just like not that much different. Like the problems that we're going to be looking at, like now, instead of just being like given energy from like the frequency or the wavelength, we're getting the energy from our transition from energy levels. You guys dig what I'm saying? It's not too terribly different. And this is all I need you to do. Your homework. What I need you guys to do is outline section 7.4, and then homeworks 24 to 34, just the even numbers. And this is why I love Bohr. Bohr, this guy's awesome. He was also a really kind and wonderful man. Everything I've ever read about him says that he was just a really generous and like warm individual, which just makes me happy to hear. A physicist is just an atom's way of looking at itself, man. That's awesome. Hope you guys have a day half as awesome as that quote, and I will see you around. I'm thinking tomorrow, 1:30 Zoomy time.